Every state Route 71 Blackbird that ever flew leaked fuel on the runway. Not because something was broken, because that's how Lockheed designed it. At Mach 3.2, the skin of this aircraft reached 1050 degrees Fahrenheit. Hot enough to cook a steak directly on the fuselage. And the entire airframe, 107 feet of titanium, physically grew by 6 inches. 6 inches of metal, expanding mid-flight. If Lockheed had sealed those fuel tanks completely, the aircraft would have destroyed itself before it reached altitude. So they didn't seal them. And by the end of this video, you'll understand exactly why that decision was the most brilliant piece of structural engineering of the entire Cold War, and why the Soviets unknowingly paid for it. The fastest jet ever built was also the leakiest, and that was never an accident. The state Route 71 Blackbird entered service in 1966. It flew faster than any aircraft before or since. Mach 3.2, that's 2,193 miles per hour. It flew higher than any operational aircraft of its era, above 85,000 feet. So high that pilots wore full pressure suits. Because outside the canopy, the atmosphere was effectively space. Most people assumed the Blackbird was a finished product. A perfect machine delivered from some impossible future. The history is the opposite. It leaked constantly. It required a fuel that didn't exist until Lockheed demanded it be invented. It needed a dedicated tanker aircraft, the KC-135Q, that served no other jet in the Air Force. It took off underfueled on every single mission, and it subjected its pilots to a violent, skull-snapping mechanical failure that engineers could never fully eliminate. The Blackbird wasn't perfect. It was a collection of accepted compromises, each one the price of going faster than any missile could follow. But here's where the engineering gets genuinely strange. What makes this even more extraordinary is where the titanium came from. The state Route 71 was built from 93% titanium. The United States had almost no reliable domestic supply. So the CIA created a network of fake front companies, names like Third Avenue Shipping and Palmer Aluminum, and purchased Soviet titanium directly from the USSR. The Soviets sold it. They had no idea what it was for. The aircraft built to photograph Soviet military installations was structurally composed of Soviet raw material. And that connection runs deeper than anyone expected, but we'll get to that later. First, the engineering problem that made all of this necessary. Here's the physics. When any object moves through air at supersonic speed, friction builds. But at Mach 3, it's not just friction, it's compression. The air ahead of the aircraft can't get out of the way fast enough. It piles up and heats. The skin of the state Route 71 on flat panels reached 600 degrees Fahrenheit. At the leading edges, the nose, the wing tips, the engine nacelles, temperatures exceeded 1,050 degrees. Aluminum melts at 1,221 degrees Fahrenheit. More critically, aluminum loses 80% of its structural strength at just 300 degrees. Nowhere near melting. Just structurally useless. So aluminum was never an option. Lockheed chose titanium. It handles heat. It stays strong. But titanium expands when it heats, significantly. A 107-foot airframe at ground temperature becomes a 107-foot and 6-inch airframe at cruise altitude. Think of laying a steel railway track in winter. Engineers leave deliberate gaps between sections because they know the metal will expand in summer. Build it rigid and it buckles. The state Route 71 is that railway track. Except this summer, arrives in 20 minutes and adds 6 inches of expansion. The state Route 71 didn't have separate fuel bladders. The fuselage skin itself held the fuel, what engineers call wet body construction. Those titanium panels that formed the outer shell were also the walls of every fuel tank on board. But the same panels that needed to flex and move during thermal expansion also needed to hold tens of thousands of pounds of fuel. Seal them rigid and the seals crack when the metal moves. Leave them loose and the fuel leaks. There was no polymer seal in 1964 that could survive both the chemical aggression of JP7 fuel and the temperature swing from -60 degrees on the ramp to 600 degrees at cruise. None. The Pratt & Whitney J58 turbines couldn't swallow Mach 3.2 air directly. Supersonic intake air had to be decelerated to subsonic speed before entering the compressor, otherwise the engine simply choked. The tool for doing that was the inlet spike, a sharp conical probe in front of each engine that moved forward and backward during flight, positioning a shockwave at exactly the right point inside the intake. That shockwave needed to sit within 1 millimeter of its target position. 1 millimeter. Miss it, and the engine experienced on start, a violent compressor stall that generated enough asymmetric thrust to snap a pilot's helmet sideways into the canopy wall. Hard enough to cause concussion. It happened regularly. All three problems, thermal expansion, wet body fuel containment, and shockwave management, had to be solved simultaneously. In 1964. By hand. But the number that really puts this into perspective is 6,000 pounds. That's how much fuel the State Route 71 intentionally left behind on every takeoff. Because the tanks leaked on the ground, a full fuel load was structurally pointless before the airframe heated up and sealed itself. So every Blackbird took off short, then immediately rendezvoused with a KC-135Q tanker at low altitude to top off before the climb to Mach 3. Every single mission started with an aerial refueling. Not as a contingency. As a mandatory step 1. That changes everything you think you know about how this aircraft operated. Here's how Lockheed actually solved it. Reveal 1. The leaking tanks weren't a failure. They were the solution. Lockheed's engineers recognized that the thermal expansion problem was actually the answer to the sealing problem. At ground temperature, the titanium panels had gaps, and the fuel ran through them. But at cruise temperature, those same panels expanded and pressed together. The gaps closed. The leaking stopped. It's the same principle as a wooden barrel. Pack the staves loosely in winter. They have gaps. Fill it with hot water and the wood swells. The barrel becomes watertight. Lockheed turned a physics problem into its own solution. Reveal 2. The fuel itself was a weapons-grade engineering project. JP-7 was developed specifically for the State Route 71 because conventional jet fuel would auto-ignite from aerodynamic skin heat alone at Mach 3. JP-7's flash point was 140 degrees Fahrenheit. Conventional fuel flashes at 80 degrees or lower. JP-7 was also so chemically stable that it couldn't be ignited by a standard spark igniter. Lockheed had to develop a chemical ignition additive, called TB, triethylborane, injected as a burst of flame directly into the engine on every start. Each J58 engine got exactly 16 TB shots per flight. Use them all and the engine could not be restarted in the air. Pilots counted every one. This is where most people's understanding of the State Route 71 is completely wrong. The popular image is a sleek, unstoppable machine that simply pointed its nose and flew. The reality, every mission was a logistical chain with multiple failure points, counted ignition shots, and a planned fuel stop before the aircraft even reached altitude. It was engineer genius wrapped in operational complexity. Reveal 3. The inlet spike, and how it changed jet engine history. The J58 engine didn't just manage the inlet shockwave. Below Mach 2.2, it functioned as a conventional turbojet. Above Mach 2.2, it partially bypassed its own turbine, diverting compressed air around the core and behaving like a ramjet. The same engine. 2 different thermodynamic cycles. Mid-flight. No other production aircraft in history has done this. The analog computer controlling the inlet spike in 1966 was solving fluid dynamics equations in real time that most universities didn't have computing power to run on the ground. And this is the detail that changes everything. The thermal expansion problem wasn't just solved at the airframe level. It was solved at the level of individual bolts. Every titanium fastener used in State Route 71 construction was soaked in liquid nitrogen before installation. The cold shrank them, made them small enough to insert into precision holes with zero clearance. Then, as they warmed back to room temperature, they expanded. They locked themselves into the structure permanently. No thread. No torque wrench. The fastener became part of the airframe through thermal physics alone. 68% of the Blackbird's outer skin was made of corrugated titanium panels, specifically corrugated to give the expanding metal somewhere to go. The same principle as corrugated cardboard. It wasn't a manufacturing shortcut. It was a deliberate thermal management structure. There are details in this aircraft that most aerospace engineers today find genuinely surprising. But here's what most people never realize. The CIA front companies purchasing Soviet titanium weren't just a clever workaround. They were an operational necessity that became an existential irony. The Soviet Union maintained global export controls on strategic materials. Titanium was one of them. But Soviet bureaucracies were large, slow, and compartmentalized. The KGB knew about American interest in titanium. The Ministry of Trade didn't communicate that to export approval offices. The CIA exploited the gap. Multiple State Route 71 airframes were delivered to the USAF containing titanium that was mined in the Soviet Union, processed in Soviet facilities, and cleared for export through Soviet government channels. When the State Route 71 flew reconnaissance missions over Soviet territory, photographing missile sites, airfields, naval installations, it did so on a frame that the Soviets had literally supplied. The fastest and most strategically important aircraft in American Cold War history was partially built by the nation it was designed to defeat. That is not a metaphor. That is the supply chain. And it raises a question that aerospace historians still debate. Did Soviet intelligence eventually understand what they had sold? And if so, did they ever attempt to compromise the material? The answer remains classified. The State Route 71 Blackbird was never a perfect machine. It was a set of accepted impossibilities, each one conquered, until what remained was the fastest air-breathing aircraft ever built. Here's the question worth debating. Given what we now know about hypersonic drone technology, should the United States have retired the State Route 71 in 1998? Or was that the single largest self-inflicted gap in American strategic reconnaissance capability of the last 30 years? Drop your argument below. If you want to understand the hypersonic successor programs and what replaced the Blackbird, I've already broken that down in full. It's right here.